So I'm just going to talk briefly about the motivation for this course. I'm just going to start from the exact same example, which we probably discussed at length in finite elements A on the linear part. Now, I'm going to come back to this. I'll probably just use black. So start from a cantilever that is fixed at one end and is loaded at this free end. You have the load to be F and the cross-section to be A. The stress in this case is going to be F over A. Now, this is something quite simple, and you would all agree on that. Now, the stress is the number you are going to use for the design. So eventually you design your beam so that this sigma should not exceed sigma y, which is the yield. I'm assuming that this is going to be steel, and you apply some safety factor. I'm going to put the safety factor in there. Usually you don't use sigma y, you would use some scaled down version of sigma y. Now, in any case, you should not exceed this number, because if you exceed the number, the beam is going to fail. This is what you do. You agree with that? Okay. Now, let us move into the three-dimensional case, the situation where you are actually going to need the finite element method. Now, in the finite element method, you don't have this, and in reality, you don't have one-dimensional problems. In reality, you actually have three-dimensional problems. So I'm just going to draw some approximation. In this case, you have the x-axis. So this is the only axis you have, and everything is living inside this one-dimensional world. Now, let us move into the real world, and in this case, we have an x, y, and z. And in this case, things are actually three-dimensional. So I'm just going to draw a three-dimensional beam. Let us assume that this is the three-dimensional beam we have. All right. Now, this is fixed at this end. Assume that this is completely fixed, this face over there. So this is the back face, and then is loaded with some uniformly distributed load on this face. Now, again, in this case, the stress is going to be some sort of resultant for this distributed force. Let us assume that the resultant is going to be, again, some F. So this is F. It represents the resultant of this force. And then you have the cross-section area for this cantilever. I'm going to assume that this is the cross-section, and this is B, this is H. And the cross-section A is going to be H times B, and the stress is always going to be F divided by A. Now, because we're talking about dimensions now, this is going to be sigma x, and this is the cross-section in the x direction. This is AX, and this is the force applied in the x direction. Everything now is happening in the x direction. Now, we are lucky because the axis of this cantilever is actually parallel to the x direction. So if you look into the axis, it's actually parallel to the x direction, and this is why we are able to use things happening just using the resultant or using the cross-section that is actually parallel to the x direction. Now, let us get into a slightly different version of this. Let us assume that the cantilever is actually standing up. So the axis of the cantilever is probably pointing in the x direction, or in the z direction, or the y direction. I've done that. I've done that in LUSAS and try to do the analysis. Now, if the x-axis, and this is in this case, or probably this is, yeah. So this is the x, this is the z. In this case, this is the z. So the z is pointing upward, and then in this case, the y will need to be pointing backward. So this is the y. All right, so this is the x-axis. I've done the cantilever. I fixed this face here. I've applied the distributed force on this free end. I calculated the stresses. I get stresses in the x direction. So this is the stress in the x direction. This is the stress in the y direction. And this is the stress in the z direction. Now, the dominant stress is actually happening in the x direction. So if you look into these numbers there, you'll see, the cross-section A was about 1, and the force was about 10. So the stress should be, in this case, 10 divided by 1 should be roughly around 1. Now, because you have some singularities in the stress at these corners, as we discussed in the first part, because you have singularities in there, the number is not going to be exactly 10. It's going to be around the 10. So it's going to be 9 point something as the minimum number for the stress, going up to 11.5 as the maximum number for the stress. The maximum number is happening at the singularities. And if you refine, you remember, you probably have even larger numbers. But anyway, the dominating stress, the dominant thing which is happening at this part is approximately 10, which is the theoretical number for the x direction. Now, if you look into the y direction and the z direction, they are pretty much symmetric. The stresses are caused mainly by the Poisson effect. You'll see that the section is trying to become smaller, but since it is fixed, is not allowed to become smaller. So you'll see some stresses resulting from this resistance of the supports, in moving in the y and z direction. So you have some stresses. Now these are secondary stresses. These are not dominants. The number is 2.7, ranging between 2.7 and 0.7 negative. So this is the problem. Now, as I said, we can play with this problem a little bit. So just use the same example, the exact same example. Now, instead of the axis being parallel to the x, the axis can be parallel to the z. And then in this case, we have basically switched the x and the z axes, and then we are going to get a very similar behavior to what we had in the previous case. However, we are replacing every index to do with x with an index to do with the z. Now, this is expected, right? So in this case, sigma z is ranging between 9 point something to 11 point something, and the x and the y are 2 point to 0 point something. Now, this is to be expected, right? Now, this is something you should have guessed. Now, I want to push this example one step further, and instead of having the axis of this cantilever to be parallel, I mean, it's not parallel to the x, it's not parallel to the z, it's at some angle to the x and the z directions. Now, this is a three-dimensional projection, but if you look into the actual case, if the y is pointing inside, so if you think about the y is pointing inside the screen, then x and z are the two-dimensional case, and the axis is going to be parallel to the 45-degree angle. So the axis of this cantilever is now at a 45-degree angle to the x and the z directions. Now I'm going to do the stresses again and find out the stresses, the new numbers for the stress. In this case, I have similar results for sigma x and sigma z, and the numbers I have are 8.5 to 4.2. Now, this is a big difference compared to before. The dominating stress is happening somewhere between 4 point and 5 point. So if you look into the majority of the stress here, which is basically the stress you are going to design for, this is around 5. We're talking about 5. I mean, before we were talking about, well, this is around 5, roughly. Before it was 10. Now, if you look into the y-axis, nothing has much changed in the y direction, so the numbers are pretty much consistent with before. Now, the big difference is in the x direction and in the z direction. So instead of having 10, we're talking about 5. So as a designer, I mean, if you have not been through this part of the course, you probably go and design your cantilever for this 5 instead of designing it for this 10. All right? All right. Now, this is a big problem. This is not a small problem. So you have been doing the finite element analysis, and the cantilever doesn't have to be parallel to your direction. It's at some angle with your direction, and you get values for sigma x, sigma y, and sigma z. How do you know what is the dominating and what is the dominant stress, and how do you know that you get the maximum possible stress to design for as a designer? And this is a question I'm going to ask you. So do you have an answer for that? So in this case, you would always know that no matter which direction your cantilever is actually placed in, you can rotate it in any angle in 3 dimensions. It is always going to be the axis direction that you look at. So in this case, I think it is relatively easy. But imagine a situation where you have a complex structure, and this complex structure is happening in 3D. So I'm just going to show a really complex structure and think about anything. I mean, I don't know, this is the famous potato in any computational mechanics book. So for example, this is fixed at this section here. It's probably fixed at this section here, and then is loaded with a distributed force that is perpendicular to the surface, probably some distributed force that is parallel to the y direction, and some concentrated force here, concentrated force here, concentrated force here. And you do a finite element analysis on this. This is the x, y, and z. Now, you do finite element analysis on this, you are going to get sigma x, sigma y, and sigma z, and you would never know if these numbers are the actual maximum possible numbers you have. So this is a true dilemma. I mean, if you don't know that, then you cannot use any of this for your design, right? And this is the real problem. This is the situation where you are going to need to figure out something to do with this values for the stress. It is actually the principal stresses, yes. So what you should be using is, you should be looking at the principal stresses, not sigma x, not sigma y, not sigma z. It should be the projection on the principal directions. Now, it is going to be difficult to imagine stress in the way the way I'm going to do or draw things is not going to be quite possible to imagine for the stresses, for reasons I'm going to come back to probably in 2 lectures once I talk about the stresses in detail. But for the time being, I'm going to talk about a force. So forces are easy to imagine because forces exist in 3-dimensional spaces. So we have, and even in this case, I'm just going to do a 2-dimensional space. So we have x and we have y, and we have a force I'm going to call F. Now, assume that F is 5. So the magnitude of F is 5, and you project this into the x direction. You have the component x to be 4, and then you project this in the in the y direction. So you have the projection in the y direction to be 3. All right. So F is actually a vector, and this vector has 2 components, 3 and 4. Now, if you calculate the magnitude of this vector, so this is the magnitude of the vector, is going to be the square root of the sum of the squares. So it's 3 squared plus 4 squared is equal to 9 plus 16. And this is going to be the square root of 25, and this is going to be 5. Now rotate the x and the y, rotate it in some angle. I'm going to call it x bar and y bar. You are going to get a different projection. So this is going to be a lot larger now in the x direction, or this is not sigma, this is f, fx bar. And then in the y direction is going to be fy bar. So fy bar is smaller than fy in the previous coordinate system, but it is still a component on f. So you keep rotating f, or you keep rotating x and y, you always get different projections for f. Now, does f actually change when you do this different coordinate system? When you rotate the coordinate system, do you actually get different forces? You are always getting the same force. However, this force is only projected into different coordinate system. So this is Fx bar and Fy bar. But if you calculate the magnitude, you would always get this to be 5, because it is always the same force, all right? See, the force is not changing, the projection is changing. So this is a vector, the components may change, but the force would always remain the same. Now, stress behaves exactly in the same way. And if you look into the principal stresses, though the principal stresses are actually a coordinate system that is projected so that the entire force is happening on the x direction, so that you project the entire 5 in the x direction, and then you have 0 in the y direction. So the principal stress is going to be a coordinate system where you have this to be 5 and this to be 0. I mean, sorry, this is meant to be the other way around. 4 and 3. So this is another coordinate system. If you calculate the magnitude of the force, you'll see that this is the square root of 25 plus 0. So this is 5. So it's still the same vector. However, the x component has dominated the entire picture, and everything is now related to the x direction. All right. So the principal stresses behave exactly in the same way, but for the stress. Now, stress is not going to be possible to imagine in this way. I'm going to come back to this point when we discuss the principal stresses in more details later on. But this is the key component. Now, if you look into the example which I've shown you, and you do calculate the principal stresses, and by the way, in LUSAS, the principal stresses are called sigma 1, sigma 2, sigma 3, or S1, S2, and S3. So the principal stresses are arranged so that the sigma 1 is the largest, sigma 2 is the second largest, sigma 3 is the smallest. And if you look into sigma 1, for the first case, when we have the axis parallel to the z direction, you'd see that the sigma 1 is again exactly the same range, is running between 11.9 to 9.1. If you look into this case, this is 11.9, 9.1. If you look into the third case, this is 11.9, 9.1. So if you calculate the principal stresses, you would always get the maximum possible stress, and the maximum possible stress is going to work for you. Okay, so you go and design for the maximum principal stress. Now, in this case, the maximum principal stress is 11.9, 11.9, 11.9. You design for the 11.9 case, and you can use this number. You can make sure that your cantilever is not going to fail. All right. Do you have any questions about this? Okay, so if you don't have any questions, I have a question for you. Let us now focus on the principal stress or the principal stresses, and let us assume that you are going to design for the maximum possible principal stress. All right, see, you are looking into the maximum. The maximum is 11.9. You take the maximum and you design for that. All right. Now, we are talking about a three-dimensional case, and let us assume that we have a three-dimensional case where sigma 1 is 10, sigma 2 is 0, and sigma 3 is 0. And then you have another case where sigma 1 is still 10, sigma 2 is 9, sigma 3 is probably 9. This is 9.5, and this is 9.0. And probably we have another case where this is sigma is equal to 10, still 10. Sigma 2 is equal to, I don't know, 8. And sigma 3 is equal to minus 9. Now we talk about maximum and minimum, not in absolute terms. We're talking about the real numbers here. Now, in all these cases, the maximum stress is 10. And if you design for this 10, you would be ignoring everything else. So you're basically just throwing away all these numbers. Now, do you think all these stresses would behave in the same way and will be always safe if you design for this just 10. It is negative. It is in tension. So first of all, we're talking about concrete. And if we're designing for concrete, concrete is a lot weaker in tension. So you need to worry about tension a lot more than you would worry about compression. So this is correct. I would say it depends really on the material you are basically designing here. Now, the stress itself, if you look into these principal stresses, we are actually projecting the stress. The entire stress is being projected into 3 directions. Now, this is why I said it is different than the forces. If you have the force, you project it into one direction. So this is the x direction, and this is the y, entirely projected in the x direction. You get the entire amount of the force active in one direction, and you know that this is what is going to affect your structure. Now, in this case, we have the stress actually projected in 3 directions. So if you look into this one, this is projected in the direction of, I'm going to call this axis x1, x2, and x3, because we don't have x, y, z anymore. We have just principal directions here. So it is going to be projected into 10 in this direction, and then 9.5 in this direction, and then 9 in this direction. If you look into the other case, would only have a magnitude in the x1 direction, and this is going to be 10. Now, this amount of stress is significantly larger than this amount of stress. So you cannot disregard that completely and move and design your structure just picking by just picking this 10. Now, as I said, it depends really on the behavior of your structure, and it depends really on the behavior of your material. So if we're talking about soil, for example, then soil is not going to be like concrete. If we're talking about concrete, then concrete is going to be different than steel. If we talk about steel, then probably we talk about steel sheets or steel bars, or if we talk about steel beams, it's probably going to be different for these cases. And if we talk about plates, then we probably talk about laminate material or composite material. So all these type of materials will behave in different ways. And some of them would behave completely different in tension than in compression. For example, concrete. Concrete is going to be quite different. So it is going to be very difficult to ignore these numbers and design only for this one. Now, there will be some cases where this number is only the dominant factor and you don't worry about anything else. But there will be also cases where these numbers are going to be quite critical to the failure. Now, it's not just that. When you project your stress into principal directions, you'd be actually projecting into the normal direction of the stress. But there will be also some projection in the shear direction. Now, the shear is also quite critical for failure. And then the interaction between the normal and the shear forces, or the normal and the shear stress, would probably be very critical for failure. So von Mises would take into consideration quite a few things here. So it would take into consideration these stresses in the x1, x2, x3 directions, and would take into consideration the shear as well, and will combine them, all of them, into one formula, and then you can use this formula for checking the failure. Now, I'm going to come into the failure criteria. I'm going to discuss von Mises in a lot more details later on. But for the time being, I want you to understand the stress to be a bit of a complex phenomenon. It's not just a number. It's something more than a number. Now, these 3 numbers, they represent exactly the same phenomenon. Now, if you look into the stress of these 3 numbers, they would probably look like this in 3 dimensions. So it is sigma 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, and 2, 3, 3, 1, 3, 2, and 3, 3. and then you project that just like you projected the force. If you remember the example of the force, I probably had it here. So if you look into the example of the force, you projected this into 4 and 3, you projected this into 5 and 0, you projected this into some fx bar, and fy bar is still always the same value for the stress, or still the same force. This can be projected into different coordinate system, and this can be projected into the principal coordinate system where you have sigma 1, 1, and then 0, 0, 0, sigma 2, 2, 0, and 0, 0, sigma 3, 3, which are basically the numbers I've talked about just above. So this is sigma 1, sigma 2, and sigma 3. Now, I'm going to explain all these things in details, just that I wanted to introduce you into this topic first and why this is relevant before we get into the content of this course. So this was just an introduction into continuum mechanics and how it is relevant to the finite element method. Okay, so don't worry much if you don't understand everything I've just said, because we are going to come back into that and explain every single bit of that in a lot more details. So I'm going to talk about the stress and the stress tensor. So it's basically these components of the stress. I'm going to come back to the hormesis. I'm going to come back to other methods to combine the stress and evaluate it. So the syllabus, the textbooks, which I recommend, are listed here. These two books are quite important. So Introduction to Continuum Mechanics and Continuum Mechanics for Engineers. So these ones are really important because I've based a lot of the material I'm going to teach on these two books. So I would certainly recommend them. I'll probably find them in the library. So the syllabus, or the material we are going to try and cover, first of all, I'm going to discuss the continuum mechanics in general. I'm going to talk about some essential mathematics. I mean, continuum mechanics would involve a lot of math. I'm going to try and stick only to the basics that we are going to require. I mean, the basic amount of math that is basically not really possible to do anything in continuum mechanics without. So I'm just going to try and stick with that. And I'm going to try and introduce it first before we get into the actual material. So this is something I'm trying to cover in the first 2 lectures. Today I'm going to cover one part, and next week I'm going to cover the second part. This is the essential mathematics. Then I'm going to talk about stress analysis, and we are going to talk about stress tensors. It's Cauchy stress tensor. This is a very specific stress tensor we are going to discuss. And this is the stress tensor that you are familiar with. And this is the stress tensor that you probably 80% or 90% of you are going to use it in real life. So I'm going to talk in quite some details about the Cauchy stress tensor. I think probably 1 or 2 weeks, probably 2 weeks for that. And then we are going to come into the strain tensor. We're going to discuss that. Infinitesimal strain tensor. This is again the one you are familiar with so far, but we are going to take time and discuss it in a lot more details. I'm just going to tell you some information about other types of stress and strain tensors, but what we are going to study actually in this course is going to be Cauchy and the infinitesimal strain tensor. And then we are going to discuss failure criteria, Moore-Coulomb. We are going to discuss Tresca. We are going to discuss Rankine failure criteria as well. And then we are going to get into the finite element nonlinear part. So the nonlinear finite element will be quite dependent on the continuum mechanics. I mean, we cannot ignore continuum mechanics. So this is why we have to do this introduction to the continuum mechanics.